Hello, we start the second part of the dynamic programming today. And firstly, we talk about different methods that contain two-dimensional searching. Um, two. Okay. And firstly, we talk, of course, we talk about different tasks that connected with dynamic programming and talk about them. Firstly, we can remember task when we have the matrix. Um, and we try to find places between this cell and this cell. Remember it? And firstly, we can set the problem to find number of ways between these two cells. A and B. And of course, we can extend this task. Yeah. For example, we can set for some cells that it is cell where we can that we can use in the path, or we cannot use in the path, as the one we draw in it, or we draw in it 0, for example. And you remember, yeah, this task, we work with it in the context BFS, I think. Yeah. And why we remember it when we talk about dynamic programming? Because, of course, we can separate this task into subtasks, of course, because, for example, for any cells here, I can draw part of this table. Yeah, it is in the table. And we can say that in this cell, for example, how we can go in this cell. As in the task, for example, we mean that we can go from the right, or from the left cell, or from the upper cell. So I can draw that if we know passes from this, from A to cell there, and we know number of passes from A to cell D. Yeah. Then we say that number of passes to a new cell, X, for example. Yeah. its number equal to sum of these two numbers. Of course, here I mean that we do not draw these numbers, and we mean that all cells can be used in the path from A to B. Okay, but of course, if we have, for example, matrix with these numbers, we can set that the matrix with the numbers will be say of E G. Yeah. So we can say that this formula changes to, for example, this, and say that we multiply by, or we can say, we can set, for example, yeah, multiply by C of C plus n of d, number of bases from A to D. I mean that every cell has two coordinates, and when I set C of C or C of D, I mean that we use these two coordinates and find a number in this matrix with these coordinates. C, this? I think it's number 1 or 0. As in this matrix. So, what's interesting in this task? We can get the recurrence formula for interesting numbers. And of course, we can use it to find number of ways from A to B with recursive algorithm. But we can see that there are a lot of subtasks that intersects because, for example, we can find ways from A to C. We need to find to this cell, and, for example, to find ways to D, I need to find ways here too. Yeah. And so, if we use recursive formula, then we twice times find ways from A to this cell, and then we can use memorization to reduce complexity of these recursive computations. Firstly, to understand, first we need to find recursive formula. In all today's task, we try to find it, and it is important for the previous tasks that we talk about in the previous lesson. And secondly, we talk about why uh, we use dynamic programming, and why some subtasks we um, we we cannot compute twice twice time. So about this task about finding the ways, I think okay, and um, and so use nation to prevent uh, repeating of the computation of the subtasks. Repeating, yeah. Computations of subtasks. So I think you know how to solve this problem, and then we talk about different problem, and we talk why two-dimensional methods interesting for us. So second task, name as edit distance. Is the distance from between two words. For example, we know that we have two words W and U, and we want to compare it. Of course, they can have different lengths, N and M, and all of these characters from A, it is alphabet. Hmm? Not what? Oh, I think alphabet is the sum set. It can be Russian language, for example, English language, or union of it, or union of numbers, and etc. So, how we can compare these words? Now I define it, and it is better to see firstly two examples, and then set the formal explanation how to find the distance between two words. Examples. Firstly, for example, we have two words. For example, union no, for example. So you can see that we can draw these two words one character under other character, yeah. And then we find characters where they are different. It is the only place where they are different. And so I say that the distance between these two words is equal to 1. But it is the only one example, and it's interesting how to find distances between other words. For example, okay. For example, winter and midterm, between these two words. And as we can see, we cannot try to write these two words under one after two, because lengths of these two words are different. Yeah. And so I can try to try this word under this, such that places where they are different will be the minimum. So I can write it. If I wrote first character after under the first character of W, then I find that difference between these two words one, two, and it is important that if the lengths are different, then we can put empty character here. We can use empty sets to imagine it, or lambda. It's not important. So the distance between these two words is equal to 3.
W and W is 0. Distance from the same word is 0.
Yeah, of course, yeah. Distance between the same words is equal to 0. And if the distance equal to 0, it is equal words. Of course, you can prove that this distance make metric space from the with the words, and because this distance we can write triangle inequality, and it will be true for this distance too. So about other examples.
So it is called Elliott distance.
I don't remember how it calls, but I think it's Levenstein distance between two words.
It is what? Sorry.
Levenstein edit distance. In the most books, you can find this task as edit distance between two words. and
And
edit distance.
okay, yes, yes. And it's only for strings, comparing two strings, or is it related somehow in graphs
No,
or something?
it's only for two words. We find distance between two words.
And in programming, when we want to make it as a program, when we want to add empty at the end of the, for example, in second example, you added empty null in the end of the first
Yeah.
word. Yes.
I write now other example in which we can add empty character in all places in the words to reduce number of places in which they are different.
Okay. Yes. Good.
I explain it now. 1 second.
Thank you.
So about the other, for example, table and and trouble, for example. For example, we can try to write this word under this word. And we find that number of characters in which their difference is equal to 6. Yeah. But the distance between these two words is not equal to 6 because we can add. We can see that if we shift these 3 characters here, they will be equal to these 3 characters. So I can say, and the distance in the definition mean that we can input any number of empty characters in each places between other characters, and after each and before characters too. So I can write that we can add empty character after A, or 2 characters after A, yeah, empty characters. And then write all the other characters. And then I write the second. And we see in which places there are difference in these 3 places. Yeah. Oh, 1 second, please. It's important to answer for one message. Okay. So the distance between these 2 words equal to 2, 3.
I have one question.
Mhm.
What if we had instead of O in trouble, it's A.
Here,
Mhm.
if we
Instead of O,
if we add A,
yes.
then we can input these two empty characters before A, and the distance will be equal to 2. If we change U with A, so we can input these empty characters in any place in the word. So
Sorry.
yeah,
Can we say that this question, this task is somehow similar to parentheses example? I mean, we iterate through first and second words to for loops, and we uh, we we consider the first letter, for example, T, as opening parentheses,
Mhm.
and the second repetition in second letter would be close parentheses.
Mm,
And we consider the least number, least possibility for the
mhm.
iteration.
You mean that this task connected with the personalization problem of what?
Uh, we said that there was a task. We said that is this string of parentheses valid? I mean, there were some open and closed parentheses, some repeated.
Um,
Um,
I think these two tasks are not connected, but we talk about uh, we talk today about matrix multiplications, and this task will be connected with two-dimensional dynamic programming, but not with this task.
uh-huh.
I think they to solve this and task with the parameterization, ah, uh, we can use dynamic programming, and we use two-dimensional dynamic programming. We use
Yes.
memorization for two-dimensional data, but I think it's the only thing that that is connected these two tasks.
Mm-hmm. Thank you.
So firstly, about the distance. I right now, what is the definition of distance between two words? Of course, it's minimum of the difference between two words. Uh, like this. In which words W and U are different. If we can add any numbers of empty characters, between characters of these two words. mhm. And before the first and after last two. Yeah, for example, we see that in this example we add one empty character in first word after the last character, but here we add two empty characters into the word. So we can add it in each place to minimize the places where they're different. Okay. So of course we can add these empty words in the second word too. And
Maybe to make sense because the second one is longer than the first one.
so I need to make a fourth example, I think. Fourth example with two words. In seconds, I need to. Mm. Mhm. Should- Uh, yeah. We can compare these two words. And what is the addition between these two words?
Eight, I guess.
Uh, I think the distance between these two words equal to 6. Because if we try to add empty characters, we see that the distance places where the difference only only uh, yeah, only improve number of these places. So for this,
Some at the left.
But I need to add as example, I think. Okay, and for example, these two words, of course, they are not in the English dictionary, but we can use it too. For example, what is the distance between these two words? Only one, yeah? One. But we can add, for example, here, we can add here, so what's the difference between these two words? No, it's equal to 1, but it's interesting due to
Two?
2, of course, yeah. Because we can add here empty character. But of course here we if we add here empty character, we have we have only 2 places where the difference.
Professor, we have to start both the strings from the beginning of each other. For example, couldn't we add empty in the beginning of the second one? Is it possible?
It is possible, of course, but in this example, we can't add it. Yeah.
But for question example number 4, is it possible to start have the first one W the same and U like empty S, and instead of, and also in the first one we have to add 3 spaces between 3 empty between E and S, and then it will be 4. Wouldn't it be like this?
The distance. Yeah, I understand you. You mean that E and S, and here empty, S,
empty.
Yeah.
E. Yeah.
E. R.
DT and E and R. And it.
But
yes.
Here we find more than 6 places where the difference.
Oh.
You can see that.
Yes.
1, 2, 3, 4, 5, 6, 7. 7 places where the difference, so it's not good. But I think if, for example, we change this word with the C, but no. We talk now about the algorithm. It's better to understand what is the algorithm than to understand in common way how to find the distance, because algorithm is more simple to us to understand than empirical ways to understand it. Because firstly, we can say that if we have two words, V and U, we can compare these two words. We can start to compare. For example, we compare first two characters. And we set two iterators for these two words. E and G. And then we say that the subtasks that we need to solve what is the distance between prefix of we or prefix with the length e of word e and so what's interesting? For example, we tried to find this number. We see that because due to these two iterators, we can say that D depends on two numbers, E and G. So it is the matrix with the answers for the subtasks. And for example, we know answers for some subtasks with the less iterators E and G. So if we add new characters UG and WE, we can say that there are three ways to compare these two words, these two prefixes of words W and it is prefix 3. It is prefix.
Without
Hmm?
prefix without empty character or prefix with
Prefix without, but when we find the distance between these two words, we can add empty characters. Yeah, and then we can say that we can add empty character over this character. We can add empty character under this character and compare these two words. And we can say that if they're equal, we can close these two words by hand and compare these two prefixes. So first way, yeah, to add the empty character over UI or UJ. So we need to compare it's W E G minus 1 so we say that distance between these two words equal to d with indices E and G minus 1 and one another place where they are different. The second case is when we add empty character under the last character of W. And the empty character under so we can compare these two words. And then we say that we add only one place where there are difference. So the distance between these two words is equal to d with index E minus 1 plus 1. And special case, oh, yeah, you see empty character. I shortly write it because of the time that we spent with it. And special case that you need to input in the if condition in the code. If they are equal, so we can compare eastwards. And because they are equal, we say that in this case, the distance between these prefixes will be equal to dE minus 1 G minus 1. And we don't need to add plus 1 because they are equal, and in this place they have no difference. So as the summary of these three cases, we can say that dg will be equal to minimum of dE g minus 1 plus 1 dE minus 1 g plus 1 if g doesn't equal to WE. And if they're equal, we can add here and I think it's the first case that we see here, yeah. In the first case, when we add character over the OG. The second case. And the last is a special case when last characters are equal. And we see that due to this formula, recurrent formula, we can solve this task with dynamic programming, with the memorization of solution of these subprograms. So I go here and example of working of this algorithm. Somewhere, okay. So we see that n equal to 6, m equal to 6. Yeah, and we want to find d with indices 6 and 6. So we need to write matrix and usually we write here characters to understand some yeah. So firstly, if we can add here empty characters, empty prefixes. And if we have empty word, we set the distance between them equal to 0. Here 1, 2, 3, 4, 5, 6. Here 2. And then we use this recursive formula to find these numbers in this matrix. Firstly, for example, here we compare E and S. We see that they are different, so we find the minimum of these two characters. It's equal to 1, and right here minimum of this plus 1. It's equal to 2. Then we can compare N and S. We see that they're different, and right here 2, 3. And for example, if we compare these characters, we see that they're similar. So to write here number, we need to find minimum of these characters plus 1 and find and compare with this character. And we see that it's less than these numbers, so we can write here 2 because of this case. Because we can say if UG and WE equal, then we can compare their prefixes without these two characters. And we repeat it for this matrix. For example, here we write 3, 4, 5. Who is different for all of these characters. So here we find M2 difference. 4, 5, 4, 5, 6, 7. Then for M compare this, we see that they're different. So we find the minimum of this to find number here. We compare these two numbers, find minimum and add 1, 5, because M is not equal to I. So we compare this number and this number and add 1. Here. We compare these two numbers and add 1. Or we can add 1 to it and then compare them. So then we compare it and add 1 because of they're different for all these characters. 5. I think that the minimum of these two numbers equal to 4 plus 1, 5. 6, 7, 8. And then we see for E, it's equal 6, 7, 6, and then we see that z equal, yeah. So we add to this number +1, 7. We add to this number 1, 7, we get 7. And then compare 7, 7 and 5 because they are equal. And we write here 5.
Sorry, why
Hmm?
when we got E and E?
Can you repeat, please?
In summer and insect, when we had E and E, we compared the previous numbers. We had 6 and 6 with +1, so we compared 7 and 7, and we compared 5. 5 is why? Why we have 5?
Yes. You're right. Then R is not equal to all of these characters too. So we write here 7, 8, 7, 6, 7, 8.
Sorry.
7, 8, yeah. And 1 second, please. Why we get 8 for this? Oh, of course. Can you turn it here? Of course, if we see this, I forget that, of course. If we compare parentheses, we need to understand that, for example, here we need to add d with these indices +1, because in these two cases we add empty characters under one character or over one character, but we can not to add any empty characters and write omega we over the character u with index uj, and so we have, of course, all right, here fourth case when we write omega e.
Can you explain that again?
Or,
What you just said.
Hmm?
What you just said.
I say that, of course, there are 4 cases. When we write empty character under omega under we, when we write empty character over u with index j, and when we write this character over this character, and they are not equal to, and the special case when they're equal, and here are not equal. e minus 1 minus 1 and then we compare these prefixes and find minus 1 g minus 1, and because of they are not equal, we add plus 1. So due to this fourth case, we need to add this number here. And so in the example, I need to erase some numbers. For example, here it is equal to 1 because of this. Oh, so yeah, we need to erase, unfortunately, all of these characters due to my mistakes. Sorry for that, but so we understand in which place we need to not forget. So yeah, we need, if they are not equal, we compare all of these three numbers, find the minimum of them, and add 1. So we write here 1, 2, and if they are equal, we compare this number plus 1, this number plus 1, and this number. So I write here 2. 3, 4, 5. So then to find distance between this character and this, compare these characters, they are not equal. So I write here 2, 2, 3, 3, because I compare all of these characters, find minimum and add 1, 4, 5. Yeah. And I repeat it. Here 2, 4, 4, 4, 5, 5. E. We compare these characters and here 5, 5. Compare these characters, they are not equal. Right here 5, 2. Then we compare E and E with, we can write here this number. Five, 6. Then for R, we compare these numbers, and add 1. Repeat it. Yeah. And it is the right answer. Hmm?
Is the last column, last line.
Yeah, it is the number in the last cell in the matrix. So, of course, we can find the, for example, way from this number to this number. So, for example, we can find when we say that it is the minimum of these three is equal to 4, we say that to find distance, we need to write one character over the second character. And then we, for example, these characters, this, and this. Yeah. So if I find this way, I can write these words with the empty characters to understand how we find distance between them equal to 6, I think. For example, firstly, we find E over S because we go from this cell to this by the diagonal way. So we go here 2 by the main diagonal of the matrix. Then I go from here to this cell. So I write M and add empty character over it. Then I write both characters. And here I write R. And you see, for example, here we add empty characters for both of the words. And places where there are difference. Are these places, and it is equal to 6, 2. But of course, we can find different ways here too. N multiplied by M. Yeah, of course. And space.
So there is no like a more optimal way to do it than M. There is no another way to do it that will cost less, right?
Yes. It is the only way to find any distance between these two words. And of course, we can find different representations in which we get the right number of places in which there are difference. For example, in this picture, we can find other way to this cell. For example, this way. And by this way, we can say that this number is the number of in which we find the difference between these two words. And it's, of course, 2 equal to 6. So as in this example, we can see that we can add empty characters, or we can not add these empty characters, but the distance or the places, number of places in which they are different will be similar. So it's about added distance, and as you see, of course, it's only two-dimensional dynamic programming to solve this task. But of course, it is important, as we see, to find the right recursive formula to it. And when you find it, you can solve a task with some memorization. Okay, now it is 5. Do we need to have break time? So I think now we have break time for 10 minutes, and after it we talk about other problems as matrix multiplications and finding palindromes. Do you know what is a palindromes? Palindrome. What? As this word, for example. If we read this word from left to right or right to left, we get the similar word. You can rewrite this word. First you write the last character, then you write the previous, and it is the similar. Name of these words. Palindrome. Did you face with these words in the other courses? Okay, we talk about this problem, and in the end of this lesson, I talk about our next 2 lessons. It will contain theory of finite automatas. Did you face with it too? No. Deterministic, finite, and not deterministic. And there are different algorithms that connected with them. And for example, in some cases, in the architecture of the computer, you can face with this of the using of DFA because of, for example, cache synchronization. There are coherence protocol that work with the that use DFA in it. So it was the second task about added distance, and we see that in some task we can find two-dimensional dynamic, and so to add other tasks that you can solve with the two-dimensional dynamic programming, we can say about finding
Why is it called two-dimensional dynamic? Why is it called the two-dimensional?
Because you can see that we need to use matrix to store the, yeah, and so it is it's knows as two-dimensional dynamic programming, and I think there are no difference between one-dimensional, two-dimensional. It's only about storing and about visualization of this program. Because when you talk about strings, lines, about words, you mean that it is a linear structure. And it's not obvious that we need to use some matrices to compare or to make dynamic, because as you remember in the previous time when we find the maximum or longest substring, yeah, we use only additional array to store information about subtasks, and then we solve it with this memorization. But now we need to use matrices to store some information, and it is important that we talk about our recursive formula for matrix elements. So you need to understand that in your task you need to find firstly recursive formula, understand is it one-dimensional because of number of indices, or two-dimensional, and so then use matrices or arrays to memorize information about subtasks. So about finding palindromes. As I say, is that if we have what we say that it is palindromous if for all e equal to 1 n, we say that this character equal to this character.
But this we can do this in linear time, right?
To understand what is palindrome or not, yeah. But now we want to find the maximum subsequence that is palindrome. Yeah. Palindromes. And for example, not palindrome. Task. Find the maximum subsequence of characters that is palindrome. And here I erase it. Substring, I think. It's more useful in this case because it means that palindrome will be a continuous part of the word. For example, here the maximum substring that is palindrome only one character, B, for example. And we mean that it is subsequence but not substring because it's not continuous. Yeah. So how to find two-dimensional dynamics here? For example, we can say that DEG, it is the answer of this task. With the input having either or W with index E. W with index G. And then, for example, if you want to find a palindrome from E to G, then we say that if we want to find the longest substring that is palindrome, we can say for this character. Firstly, we can find the maximum palindrome of these substrings. I mean that, for example, here omega W is index K, and so we find DG as the maximum for index K that is bigger than E, less than G, and it is DE K, I think. But it is possible that the maximum palindrome will contain this part of the words. So we need to add here we need to DG is the maximum of these numbers of maximum where K bigger than E and less than. And these two cases are cases in which the maximum substring that is palindrome doesn't contain omega or W with index G, or doesn't contain omega with index E. And we have one case when it can contain these both characters. When when answer for D of E plus 1 and K is equal to difference between these numbers. So I need to plus comma and 0 or G minus E plus 1. It is if the answer for this subtask is equal to difference between them. This one. Plus 1. And otherwise 0. So we see that, for example, if we know the answer for this subtask, we know the answer for the question. So, how to understand, how to compute it? It is interesting that I think that, yeah, here in the previous task and as in the first task, we go from this corner to this corner, yeah. But in some two-dimensional dynamics, you can use your algorithm as waves from the different point of this matrix, not from this corner or this corner. You can use it, for example, from diagonal. So, to understand, we write here example. If we have, for example, A. So, I write here matrix 1, 2, 3, 1, 4 times 4. And we know if we find, if we try to find D with index EE, it is equal to what is the maximum palindrome of our word with one character. Yeah, if we have only one character, for example, A, it's 1, yeah, the length of the maximum substring that is palindrome. So I need to write here 1, 1, 1, 1. Okay. And then I can say that for two words or for two characters, I can find the answer. For example, for this word, I can write here 1, 1, 1, 1, 2, 2. And this is the initial part of our algorithm. It's the base of it. Because then, to find, for example, and of course, it is symmetric matrix. I mean that if I try to find DE, it's equal to so it's not important to find these elements or these elements. So, for example, D with index 1 and 3. 1 and 3. We see that here. Yeah, it's the maximum of D with index 1 and 2. 1 and 1. With index 2 and 3. 2, 3, 3. And then I see that they are equal. So I add here 2 with index 2, 2 plus 1. And then I see that it's equal to, no, not this, but their difference, G and E plus 1. It's 3. So I see that we know D with index 1, 1 and 2, 2, 3, and 3, 3, yeah.
I mean, why 3?
Hmm?
Why do we have 3 at the end?
Because of this. Because of this. And you see that it is two special cases. When we find this equal to, when we say that, okay, if it is palindrome, we can extend it with these two characters if they are equal. So I write here 3, and of course, maximum is equal to 3. And you see that we use information in this matrix from this and from this cells of the matrix. So then we can repeat it, for example, for this cell. Yeah. We can compare these numbers, we find the maximum, it's equal to 2. And we see that 2 and 4, C and A is not, they are not equal. So I cannot add this number here. So I add 2 here. And then I find the maximum of this part of the matrix in this part of the matrix, and it is equal to 3. And so the answer to our question, what is the answer to our question? The maximum parameter from 1 position to n position. D with index 1 and n. Yeah? Here. It's the answer for our task. Because the answer, if we talk about whole world, so it means that we start with the first character and we end with the n character. So it is equal to D with index 1 and n. For this example, it is equal to 1 and 4. So it's about dynamics. If we you see that if we find correct recursive formula, if we understand how to divide it to the subtasks, of course, and use right structure to memorize the information, so we get the answer by the dynamic programming, by the using of it. And for example, what is time complexity of this algorithm? Space is understandable. It's equal to O from n square. No. We repeat our recursive formula for all of these cells. Number of the cells is equal asymptotically to n in square. And you see that for all of these cells, to find the number, we compare this subpart of matrix and this subpart. And it is 2 n asymptotically. So it is equal to O from, we repeat n times for these numbers, or step that spend our n time. So it is n cube, yeah. But of course, it is more comfortable than to compute it by the finding all of the substrings and compare them. Is it palindrome or not?
Sorry, but for example, the cell in the matrix D21, how did we fill it with 1? According to what?
With which indexes?
D21, or for example, D43.
I think
D4.
it's two special cases. When we have two characters, we can compare them, and if they're equal, we set the number in this cell equal to 2, as in each in these cells. And if the characters are not equal, so we set 1. So we can compute it before we start common case and compute all the other numbers in the matrix.
I get it, thank you.
So, as you see, we find substrings. And of course, you can say that, okay, if you want to find substrings, for example, we can set iterators, try to understand, is it palindrome? We spend 2 O from n time, and we repeat it for all substrings. So asymptotically, it is equal to O from n cube 2. But, for example, imagine that if we change substring with the subsequence, if we try to, if we change substring with the subsequence, for example, why it is different? Because forward the longest substring, that is palindrome, is equal to 1. But subsequence, what is the longest subsequence of it?
3?
3, ACA, yeah.
Or ABA?
Or ABA, yeah. So, of course, it is the other question, if we change substring with the subsequence here. And if we try to use native algorithm to count all of these cases, how many subsequence do you know in the word with n characters? 2 power n. And so native algorithm has O from time complexity. And it is exponential time. But for example, we can see here for recursive formulas. And we say that, for example, we can change it in some places. For example, we need to change here this formula, because if we know that they are equal, so we can find subsequence in which here we find palindrome and we add to it these two characters. So we need to change with it with the 0 or d e plus 1 g minus 1 plus 2 if they're equal or otherwise. Okay, and I think it is all that we need to change here. Because now we can find the answer for this question by the two-dimensional dynamics as the previous. Yeah, I said initially it's equal to 1, or this equal to 1 too. And then I see, I compare if I start with A and with B, I compare them, they're not equal, so I find the maximum of it, of these numbers, and it is equal to 1, 2. Then I see here from C to A, they're not equal, so I set here 1, 2. And then if I compare last character with initial character, they're equal. So as we change here, if they're equal, so I add to this maximum, add this answer for subtask with plus 2. So the answer for this subtask is the answer from C to B. Yeah, it's equal to this number. So I compare 1, 1, 1, 1, 1, 1, and 1 plus 2. So I set here 3. Yeah. So it is the answer for this algorithm. And as you see, we change nothing in the algorithm, but we change recursive formula. And it's interesting that if we use dynamic programming and we can change the input data, for example, we change substring with subsequence, and we can change recursive formula with other recursive formula and change nothing in the program. So it is very useful that, for example, and that we talk about in the code review, that you need to write code in which if you change one algorithm to other algorithm, you change very little lines. So here, for example, we change only 3 lines, I think. And then our algorithm come with the same time complexity, of course, yeah, with the time complexity equal to O from n cube, yeah. It is better than exponential time, of course. We solve this task. And it is important that if you to solve every task, if you change all of your code, it is complicated to you. And you spend a lot of time to understand that you need to change, to make this function. But if you have abstract, for example, structure or abstract data that explain your solution, for example, for dynamic programming, in every task with the dynamic programming, we have recursive formula. And we have subtasks. And for example, for previous subtasks that we talk about, we use arrays. For this, we use matrices. And of course, we can make abstractly structure that contain additional memory that we use to memorize and that contain method with the recursive formula, and that contain way that we use to find the answer for our task. So, for example, in this case, if we have these 3 methods, yeah, imagine that we implement solution with the structure that contain, for example, M matrix with the answer for the subtasks. For example, not well, I think it's in function to find new elements of the matrix. Use recursive formula. And for example, methods that contain a way that we find elements in the matrix. I think, yeah, it's 2. And, for example, compute way that we go through the matrix. So, for example, for previous tasks, here, if we change substring to subsequence, we change only this function and nothing other. Yes. In every task, understand that if you get the other conditions, other parameters, for example, if you change some parameters in the task, how many lines will change when you solve it. So it is empirical way, of course. And now I think we want to solve other tasks. And now we spent 6 hours. Okay. So other tasks. That are very important or in the way to understand dynamic programming, and important to understand in which places it is necessary to understand that we spend some time to computations. For example, first task here, it's the matrix multiplications. If we have, for example, some matrices, and we know that this matrix has a size equal to pi minus 1 pi, and we need to understand what is the first multiplication, what is the second multiplication, and our task here find the way to multiply all of these matrices with the minimal time. So, for example, if we have only 3 matrices, for example, to 100, there are 2 ways to multiply it. And so, if we multiply A1 and A2, we spend how many time we spend for it? what is the size of their multiplication? 2 and 200. Yeah, so here we spent 200 multiplied by 100. I erase here with 1. And then we multiply matrix 2, 20, 3. And in this way, firstly, we multiply these two matrices, and we spend 100 multiplied 20 multiplied 3. And then we multiply these two. Because remember how we multiply two matrices. If we have matrix NM multiplied by MK. As a result, we get N multiply K. And to find only one element, we spend O from M time. Because as you remember, in formula, we have a summary of multiplication of these elements and these elements. And so, how many elements here and here? M. And we find multiplication, pairwise multiplication, and sum of it. So we spend O from M time for all the elements, so we multiply by NK. And then, when I multiply A1 and answer for the first multiplication, I spend so we can compare these numbers, and we see that here we spent 40,000, I think, 40,000, and
Here it was 200 instead of 20, but when you change it, you didn't change it.
Oh, yeah. You're right. So it is equal to 4,000. And here what is the answer? And you see that the answers are different. So we want to find the minimum answer for this multiplication. So it's interesting that to find the answer, we can use the similar formula as for the previous task. We can say that last multiplication can be between what is the last multiplication? Is multiplication between the answer for these multiplications we said is this, and the answer for this multiplication. And then we need to sum these time complexities and add the time that we spend to multiply all of these matrices, or multiply this matrix and this matrix. So I said here give 0, 1. So for AK is equal to AK here. So we spent, I think, previous 0 multiply PK multiply Pn. And of course, if we want to minimize our time complexity, we need to find minimum of these numbers. It is the answer 1a. So you see that it is similar that we used to find the answer for the first task, or for the previous task. Yeah, as here. Yeah. So for this task, we can use the same way to go through the matrix. We start with the diagonal matrix and go over it by the diagonals. So do you need to compute it for one example? So as the example for working of this formula. For example, if we have matrices A1, A2, A3, A4, for example, these sizes. And then we set the matrix in which we memorize information of the subtasks. As you see that we don't need this part of the matrix. And for example, if we have D with the same indices, E and E, how much time we spend for computation it if we have only one matrix? Multiplication. No. We have the answer in the initial point of our task. So we cannot spend anything. If you have only one matrix, for example, N1, and you need to find multiplication of this matrix, you don't, you have the answer. It is the only way to find it. Okay, so for example, here 1, 2, 3, 4, 1, 2, 3, 4. Yeah. For example, 1, 2. To find it, we see here, and we see that the only way to divide it into two parts, it is divided to D11 plus D22 plus then multiplication. So we multiply 2 times 203. It's equal to 1,200. And then we repeat for these two matrices too. Yeah, we get multiplication of this. Oh, it's equal to 60,000. Multiplication to hundreds, 100, 100, and 3. And for this we got only, we got only 300. And then to understand how we can compute easily this task, we see that we can divide D13 minimum D12 plus, if we divide here, plus 2 multiply 3 multiply 100. Or we divide with what we said here, D11 plus D2 3 plus D2 3 plus 2 multiply 200 multiply 100. I think here -1. Yes. So we found the minimum of this summary, and we see that the minimum if we add this multiplication to this number. So it is equal to 108 1,800. And here we can add multiplication of these two. On these two, here we spent 3, 3 multiplied to hundreds, 60. Right? As in this minimization, I say that the minimum way is to multiply firstly these two matrices and then multiply the answer for this multiplication and A2. And then for this element of our multiplication, we need to compare three numbers. We need to compare if we multiply firstly this, what? And then multiply, we know d1, 3, it's equal to this number, and add 200. So if we multiply this firstly, so then we can multiply firstly these numbers. We spend d1, 2 plus d3, 4, 1, 2, and 3, 4. It's 1,500. And then we spend 2 multiply 3 multiply 1. Only 6. And then if we divide it to this part and this matrix, we spend for this d with indices 2 and 4. Plus the multiplication 201. And we see that the minimum is 1,300. Yeah. So we see that in this case, it is better to set the parentheses here and to find 2, 4, we firstly multiply this two matrices and these matrices. And it is a way to multiply them. Okay, it is understandable. So as you see, the way to find the answer is the same. But we change only recursive formula. So for this task, for the previous task, if we see as programmers here, we can see that there are 3 main parts in it. And the only way, part that we change is the recursive formula. So it is very useful that we can solve different problems with the same structure. Okay. I think now it's very a lot of time. So some words about the second task. It is knapsack problem. Do you know what is this knapsack problem? For example, if you have some stones, for example, with the weight and values. And you have backpack. And you want to add these stones in your backpack. And you have restriction to the weights of the sum of the stones. You cannot add the stones with the weight more than W, big W. And you want to get the maximum value. In the common way, this problem is the NP full. Do you know what is NP full problem? Yeah, NP complete problem. But in some way, we can solve it, for example, or with some restrictions. Solve it. For example, if we said that weights is integer, number and we have infinite number of the stones with one type. So we have finite number of types of stones, but we have not only one stone, but it's number of stones. Of which type? So we can get, for example, 5 stones with the weight W1 and value V1. So to solve it, you can use two-dimensional linear programming. And you think about it at home, I think, because now we have no time to solve it. As you see, for example, in the common way, knapsack problem is very hard to solve, and we don't know how to solve with the polynomial time. But for example, with some restrictions, we can solve it with the dynamic programming. You need to understand what is the matrix that we use to solve it, and what is the recursive formula that we have here, and then you use the algorithm that we talked about previously. So I think it's all about dynamic programming that we want to talk about. And next time we start with the deterministic finance automatas, and we talk about it, and then talk about Knut-Morris-Pratt's algorithm. Did you face with it, Knut-Morris-Pratt? Yeah.
But we didn't study.
Didn't study. Okay, so we study it next time, I think. And we talk about common theory of DFA in it, because DFA is very useful in the realization of the programming languages, because some lexical analyzers use in its DFA, but of course they have very complicated structure in it, but as if we try to if we try to see with first view on it, so we see that it is similar to DFA, because when your lexical analyzers see your program, for example, and see, okay, that is the start of the program, we see that is type integer, for example, this name variable, and for example, for C++, we need to find the end of the string. It's the point with the comma, yeah. And lexical analyzer change the condition with finding new elements, and it is connected with the grammatics, and I think we talk very quickly about it, but it is very strong theory, so it's interesting for us too. So that's for today.